Hey guys, this video is about the different things you can do to manipulate K, the rate constant, and the different scenarios you might want to do that in. One concept that you need to understand is that the overall equilibrium constant for a series of chemical reactions added together is the product of all of their K's. An example of what I mean is, let's say you have the reaction N2 gas, nitrogen gas, reacting with oxygen gas to produce nitric oxide gas. And the K for this reaction is 4.3 times 10 to the negative 25. And you have a second reaction. Two nitric oxide molecules may actually react with oxygen gas to produce two molecules of NO2, nitrogen dioxide. And the equilibrium constant for this reaction is 6.4 times 10 to the 9. Well, if you wanted to add these two reactions together, and by doing so, look at this reaction, could you do so theoretically? Yes, you can. And what do you do to these K values to get the subsequent K? Well, according to our rule above, the actual overall K for this new summation would be, so the K for this reaction is 4.3 times 10 to the negative 25 times 6.4 times 10 to the positive 9. The sum of the K's for the individual reactions. That value is 2.8 times 10 to the negative 15. Another thing to consider is what happens if you want to reverse the direction of a reaction. What happens to its value of K? Let's take this reaction here. Two SO2, sulfur dioxide gas molecules. They can react with oxygen gas to produce two molecules of sulfur trioxide gas. To some degree, because this is an equilibrium, we could have written this reaction the other way. We could have written it with the SO3 as the reactant and the SO2 and the O2 as products. How does that affect our value of K? Let's think about this. Writing our equilibrium expression, SO3 is raised to the second power. SO2 is raised to the second power, and we multiply that by O2. If we had written this in the other direction, and we had called SO3 the reactant, and SO2 and O2 the products, we would have written K as O2 times SO2 squared divided by SO3 squared. When we look at these numbers, what becomes kind of obvious is that these are 1 over the other, to go from one direction to the other. if you actually think about plugging real numbers in, these are the reciprocal. So if you want to go one direction versus another, depending on how you want to write a reaction, you simply do the reciprocal of the K. Another way of saying this is K forward for any reaction approaching equilibrium or at equilibrium is equal to 1 over K reverse. So the forward is equal to 1 over K reverse. So if in the process of manipulating reactions you want to write them in the other direction, you simply do the reciprocal of their value of K. A third type of manipulation that we might consider is, what if we want to change the coefficients of a balanced chemical reaction? The one we're looking at is instead the same reactants, but the ratios have been, in this case, let's say, divided by 2. And in this particular case, SO3 is shown as SO2 plus 1/2 O2. So what we've done here, in essence, is we've multiplied everything by 1/2. We've multiplied this reaction up here by 1/2. So if we do that, what do we do with the value of K? Well, K new, the new value of K is the old value of K, whatever that was for this reaction here, whatever our value for K was, now raised to that power. If instead of multiplying by 1/2, we wanted to instead, let's say, multiply all of these by 4. 4, 4, and then this becomes a 2. If we've multiplied everything by 4, then this new K would be the old K raised to the 4th power. So when you multiply through by a new set of coefficients, you change the K by raising it to that new power. One last consideration is pressure versus molarity units. Let's take this reaction. 2 moles of nitric oxide gas reacts with 1 mole of oxygen gas to produce 2 moles of nitrogen dioxide. We can express K in molarity units. We can express each of these substances in molarity units. And when we do, it's just really the normal K. It's the one we've been talking about, since the beginning of these videos. And it's often, if you need to, used as a K sub C. But really, K without any units whatsoever, it's assumed to be concentration units of molarity. However, one could see how instead of molarity units, we could actually express these as pressure units. And instead of using molarity, we could express this in terms of partial pressures, because the pressure of a gas exerted is directly proportional to the number of moles of gas there are in that given space. Therefore, the equilibrium expression could also be written in terms of partial pressures of gases. So partial pressures of gases in ATM units in particular. we could express this as the partial pressure of the NO2 gas divided by the partial pressure of the NO gas squared times the partial pressure of the oxygen gas squared. ATM units instead of concentration units. One could also ask, well, if I have ATM and concentration units, can I interconvert between them? And yes, you can. Kp and Kc can be interconverted following this formula. You can look in your book for the derivation, but the formula is Kp is equal to Kc, the equilibrium constant in normal molarity concentration units, times RT raised to the change in the number of gas molecules. R here is 0.0821, and T is the temperature in Kelvin, and Kc is the equilibrium constant, and delta N is the change in gas molecules, and we almost always express delta as products minus reactants. So in this case, it's the number of gas molecules of, or moles of gas molecules of products minus the same reactants. And in this case, if your reaction has the same number of gas molecules as products and as reactants, your delta N is 0, and of course anything raised to the 0 power is 1, right? Anything raised to the 0 power is 1, so this whole term would go to 1, and Kp would equal Kc in that case. A specific, to use the example that we've started with here, 2NO gas plus O2 gas, 2NO2 gas. In this case, our delta N is equal to final minus initial. So here, 2 moles of gas are our products, minus 2 plus 1 mole is 3. So our delta N is minus 1. So in order to interconvert between Kp and Kc units, you would take whatever the value of Kc is, multiply it by R, 0.0821, times T, the temperature in Kelvin, and then you would raise that to the negative 1 power. Of course, you could go in the opposite direction. You could have Kc as your unknown, and you could have a Kp, and then you would just plug in there and rearrange as necessary. So that's how you manipulate Kp and Kc, as well as K in different variables in different scenarios.